Right. Welcome everyone for the SIP seminar. It's an Inspire Lab seminar, and it's usually run by Professor Wahid Bajwa. And this year it's going to be run by me, or at least this semester is run by me. My name is Amina Sholyanin, and I'm happy to be your host. And today we are very happy to have Swanand Kadhe. He is a long-time collaborator and friend. We first met about 10 years ago, maybe 8 years ago. And Swanand did his PhD at Texas A&M, and that's the same as Professor Elrio Heb and Professor Spasojevic and yours truly. So in that sense, we also have a connection. Swanand, after his PhD, went to Berkeley to do a postdoc. And these days he is about to make another transfer, and that is to IBM Research. And he worked on very many different areas and had multiple job offers, research labs, etc. So without further ado, I'm going to ask Swanand to give his talk. Thank you very much for visiting us, Swanand.
It's completely my pleasure. Thank you so much, Amina, and everyone, for first of all for the invitation and for kind introduction. I am really excited to talk about some of the things I have been recently focusing on, in particular, secure aggregation protocol for privacy-preserving federated learning. And in the process, I'm going to tell you about a novel secret sharing scheme. It's kind of an interdisciplinary talk where I'll be talking about privacy, security, as well as some machine learning. And this is a joint work with Nivet, Ozan, and Kanal. Before I begin, let me mention that please feel free to stop and interrupt me if there are any questions. It's okay even if you shout from the Zoom in case it's difficult to see the hands. I have kept the slides modular, so let's make it more interactive than I'm talking about. All right, so let me begin. And before I mention to you about the privacy or secure aggregation, let me start with federated learning, which essentially a novel distributed learning paradigm, which has recently attracted significant research attention. So most of you may be aware with federated learning, but what happens here is there is a central server who coordinates with a bunch of clients to learn a machine learning model. So it's essentially a distributed training paradigm. And it's an iterative training process wherein in each iteration, what the server does is it sends the current neural network parameters to the client. So these are weights and biases of the neural network or any machine learning model for that matter. And then what the clients do is they're going to locally train the data model using the data on their device. And this local training can happen using any optimization algorithm. Typically happens with stochastic gradient descent. After each device makes several epochs of SGD or any other optimization process, then the devices send back the updated models, which are aggregated or averaged at the server to get the improved quality model. And this process is iterative, so it keeps repeating. So a nice feature about this federated learning distributed training is that the data always lives on device. So we're never sharing our data with the server. So it is considered as a privacy-friendly training process because we're never sharing our data with the server. But the question is it sufficient for privacy? Or the server still can learn something about the clients of the users? So it turns out that the models do leak information. In fact, some of the models can even memorize the data, and it is not at all privacy friendly. In fact, the server can learn a lot just by seeing the model updates. So let me highlight this issue by taking a toy example. And for this, I'm considering an app, let's say next word prediction, right? We have been using this in our emails or mobile keyboards, and how Google trains it is via federated learning. So let's consider the case where, let's say this is the model trained on my device in a given iteration, which I'm going to share with the server, and server is going to aggregate the models from all different users. But what if the server is honest but curious, and it tries to infer some information about my data from the model which I have shared with the server? So in particular, what if the server tries to query this model? And if it queries some innocent looking sentence, it's fine. But what if it queries something like this? Right? Swanand's SSM is. And if the model essentially gives some correct looking numbers, it's definitely scary. And I'm not cooking up this example. In fact, this paper indeed showed that deep learning models can memorize data. And you can do this inference attacks based on just the model parameters. This is just one kind of privacy breach. There are other ways the leakage can happen, and different types of attacks can be done only by knowing the model parameters. So even if the data stays on device, sharing the model with the server leaks information, and we need to do something about privacy. So the main issue with privacy is coming up because we share our models with the server as it is, right? So how can we get around that? So what I'm going to talk to you is a secure aggregation protocol. So if we can encode our models, so each device somehow encode or encrypts in certain way the models in such a way that the server can compute the average or summation without learning any individual model updates, then that's very good, right? So essentially, this is a clean problem we have. We're focusing on one iteration of federated learning. And each device has model parameters. You can think of it as a high dimensional vector. And the goal is to somehow encode or encrypt this model parameters in such a way that the server should be able to compute the summation without learning anything other than what the summation reveals. Right? So this is the problem that we are going to focus on. And in fact, if the aggregation happens across thousands or tens of thousands of devices, then the server learns much less about any individual device. In fact, this can be composed with differential privacy to enhance privacy guarantees as well. But my focus in this talk is going to be on secure aggregation. So before going into any details, let me pause for a minute just to understand if there are any quick questions. It's still high level. I'll give you more details on the problem as well as our solutions. But let me take a quick pause just to make sure that we are all on the same page and we understand, at least at a high level, the problems that we are going to solve in today's talk. All right. So as you can see, the secure aggregation. Is there a question?
Yeah, I would have a question very briefly. Mm-hmm. So the idea here then is that when the server kind of receives this computation, it doesn't actually see these WI values at all.
Correct.
Yes. Okay.
Yeah, so we have to somehow encode or encrypt them. I mean, when I say encryption, this is not some standard public key or secret key encryption. We have to do it carefully in such a way that from this encoded or this locked values, the server can still compute the summation, but it doesn't learn anything about what is inside these locks.
Okay, thank you.
Sure. Yeah, and we can define this formally, and I'll do that later, like what do we mean by security and other things, but at a high level, we want to keep this neural networks inside the lock. So as you can see, secure aggregation is a secure multi-party computation problem, right? Each party here is having its input as a high dimensional vector, and you want to compute a function, which is a summation function. So MPC has been a long-standing problem in cryptography and system security community. So what is new here? In fact, this machine learning setup brings its own unique challenges. So let's try to understand them in a bit of detail. So the model which we are going to consider throughout the talk is that our server is honest but curious, meaning that it follows the protocol honestly, but it is curious about the machine learning models of the devices. And the server can in fact collude with a subset of parties. And the server colluding with a set of parties shouldn't learn anything about the model updates or the model parameters of honest other parties. And the key challenges here comes from the scale. So first of all, we want to do secure aggregation over thousands of clients. And these are machine learning parameters. So there are billions of model parameters. So the sheer scale makes many of the classical cryptographic protocol infeasible in this setting. Also, there are going to be dropouts because these often are mobile or wireless devices, which there can be outages, there can be device failures. In our next word prediction example, if my phone gets a phone call, then Google should stop doing federated learning and I should attend to my phone call. So in that case, I drop out from this training process. So there are dropouts, and we want to ensure that the server can compute the summation even when there are dropouts. And as with any practical scheme, it's great if we can design schemes which can achieve trade-off between the requirements and the cost involved. So achieving this at this large scale makes this problem very challenging. In particular, what we are going to focus on is a typical machine learning setup where the number of model parameters is much larger than the number of users. So think of it as millions of model parameters and thousands of users. So how can we do the secure aggregation in a scalable manner in terms of low computation and communication costs? So this is going to be our problem for this talk. So what's the issue with conventional secure aggregation schemes? Right? The main problem here is that majority of the secure aggregation schemes, they either rely on homomorphic encryption style cryptographic ideas, which are computationally very heavy, or they rely on secret sharing, which also is fairly heavy in terms of computation. In fact, for secret sharing, the computation grows quadratically in terms of a number of users, and this limits the scalability of secret sharing to the large scale of applications like federated learning. So in case you're not aware of secret sharing, let me just give you a very high level black box overview. I'll go into details of secret sharing later in the talk. So here, just treat it as a black box overview where what you want to do is there is a secret, which you can think of it as a binary string, which we want to share to a bunch of participants with two requirements. So the first requirement is security requirement, meaning that any subset of users, some design parameter T users, should not learn anything about the secret. And even if any D users drop out, we should be able to recover the secret. So just as an example, here the number of users is 3. And let's say I want security to be 1, meaning that any one user doesn't learn anything, but any 2 users, we can recover the key exactly. So if we have such a scheme or algorithm, which we call secret sharing, then it is possible to do secure aggregation. And for now, take it as a leap of faith, but I'll explain to you towards the end of the talk how we can use secret sharing to do secure aggregation. But it uses fairly standard machinery from multi-party computation. So for now, just take my word that if we have a secret sharing scheme, we can do secure aggregation. So suppose we want to do secure aggregation using secret sharing, right? And let's try to understand in terms of concrete numbers. Suppose we want to cater to 10,000 clients, and let's say our deep learning models have 1 million parameters each. So that in that case, if we use a secret sharing algorithm where each user will treat its model parameters as secrets and share it with other users or clients. And let's choose the security threshold to be 10%, right? So this 10% or any 1,000 clients shouldn't learn anything about the secret. So this is motivated from the practical requirements of Google and other companies. This is a design parameter. We can choose it separately or however we want. But once we fix the security threshold, then the conventional secret sharing, the dropout threshold is fixed, meaning that what happens is any 1,001 clients, you can completely recover the secret, meaning that any 90% clients can drop out and you can still recover the secret. However, the issue is the cost of recovery, which is quadratic in n, and n here being 10,000. It's almost 0.1 billion arithmetic operation or flops that are required to do the recovery. So this is what restricts the scalability of secret sharing to the application like federated learning, where in fact the secrets are also going to be millions of parameters. Right? So the question we ask is, do we really need these strong guarantees in terms of security as well as recovery? So first of all, we cannot compromise in terms of privacy or security, because privacy attacks are often inflicted by adversarial users who can collude with each other. On the other hand, dropouts often happen due to natural or non-adversarial reasons. As I mentioned, if my phone gets a phone call, I should stop doing federated learning. So what if we keep the security requirements as strong as possible, worst case, but we relax the recovery guarantees from worst case to average case? Can we gain in terms of compute costs and communication costs? And that's what I'm going to show, that relaxing the dropout tolerance from worst case to average case allows us to reduce the cost by orders of magnitudes. And what we are going to do this by proposing a novel secret sharing scheme, which we call FastShare. And I'll spend a decent amount of time explaining the main ideas behind FastShare. I'll also highlight how to use FastShare to do secure aggregation. So let's go back to our toy example, right? And let's see how FastShare can allow us to reduce compute costs. So I'm keeping the same example where there are 1,000 clients and there are a million parameters in our machine learning model. And let's keep the same security requirement, right? Any 10% of the clients, even if they collude, they shouldn't learn anything about the model of other clients. But let's relax the recovery requirement. So now what I'm asking is that I should be able to recover this key or the secret from even when 10% of clients randomly drop out. And this is very practical number. In fact, Google, Apple, and other companies have observed that usually 5 to 10% clients drop out during an iteration of federated learning. So when we relax the dropout constraint from worst case to average case and also reduce the strictness of how many failures we want to tolerate, it was 90% before, now I made it 10%. Then it turns out that we can design a secret sharing scheme, and I will tell you how, with the compute cost of recovery being 1,000 times smaller than a conventional scheme.
I have a question, sorry. I'll turn on my camera.
Sure.
Okay. No, I think I'm not quite understand. I just somehow do, there's one bit I just don't understand.
Yeah, please.
So you're saying if so is it even if so the recovery is it conditional on the average case, like, you know, you're going to flip a coin for every coin, let's say they drop out.
Correct.
So it's
exactly. So I mean, I'll mention this in a slightly more detail in a couple of slides, but let me take a preview to say that worst case recovery is like a Hamming channel or adversarial error erasures. And what we have here is like a BEC, binary erasure channel, where each client kind of drops out with probability 10%. Right?
I'm a big fan of the Shannon-Hamming dichotomy, so exactly. I'm excited.
But the main point here is we want to keep worst case security guarantees, right? So that's why we cannot just use any the nice LDPC or any some efficient erasure code or any scheme and just you plug and play here, because we want to keep security requirements to be like Hamming or adversarial worst case, but the recovery or dropout requirements are now stochastic.
Okay, cool, thanks.
And in particular, we can reduce the cost from order n square in the conventional schemes to order n log n, right? And this reduction in cost in terms of secret sharing directly translates into reduction in cost for secure aggregation. And I'll mention how to do secure aggregation using secret sharing toward the end of the talk. Again, take my word for it for now. But the take-home message from this slide is, let's say n is the number of users and L is the number of model parameters. Then if we compare it with two state-of-the-art works, then the Google's protocol is kind of factor n slower than our protocol. So n, remember, is number of users, which is in terms of thousands. So we are at least, I mean, if you're aggregating or 1,000 or more users, we are at least 1,000 times, or even the gains grow with the number of users. So that's the gain in terms of compute cost. The communication cost remains order-wise same, right? And since L dominates n, you can think of it as it is order L cost. And in fact, even when there is no secure aggregation, you have to send your model parameters. You need to upload it to the server so that server can aggregate it. So even without any privacy requirements, the communication cost per client is order L. So in fact, we don't increase communication cost at all, but we reduce the compute cost as compared to the prior art by orders of magnitude. And with respect to a recent protocol, we reduce compute cost by order log n, but we can see that the communication cost for them is much larger. It's log n multiplicative overhead, which turns out to be very bad. And also the number of rounds is large. But this work did a great job in reducing, this is from a group of Salman Avashtimer, where they reduced the compute cost at the server at the expense of slightly blowing the communication cost and the number of rounds. What we can achieve is we reduce the compute cost further without increasing the communication cost and keeping the number of rounds to be very small, 3 rounds. And I'll give you the details of all of this in the next 20 minutes or so, but this is the take-home message of the work. All right, so let's see some of the key ideas how we achieve this. And I'm going to partition this talk into 3 phases. The first phase is going to be the novel secret sharing scheme, FastShare. And that's where I'll spend the bulk of my remaining time. And I'll tell you how to use secret sharing to do secure aggregation. And then I will tell you what are the challenges in machine learning which you need to account for to use secure aggregation in federated learning. So let's begin with the novel secret sharing scheme. And here, let me mention the secret sharing setup in slightly detailed manner, where this is the formal setup that we have S secrets. So each of the S secrets are elements from some finite field. In case you're, don't worry about finite field, just think of it as integers modulo some large prime. And we want to share this S secrets to N clients. And a toy example is coming up very soon. So don't worry about the notation. In such a way that there are security requirements. In other words, any T shares should learn nothing about the secret. And I'm considering information theoretic security here. In other words, any subset of T shares should be statistically independent of the secrets. And for recovery, I'm considering this binary erasure channel type of model. In other words, each share can drop out independently with probability D over N. And we want to make sure that we can recover the secret under this channel with high probability, where the probability of success in recovery is on the randomness of dropouts. So these are the 2 requirements. A quick word is this recovery requirement is where we differ from the classical works of Shamir and others, right? So Shamir and on almost all the works in crypto and information theory community, majority of them, other than for wiretap channels, they rely on the recovery also in the worst case, but we are considering recovery in a stochastic sense while keeping the security guarantees worst case. So there is no Shannon channel here. So the adversary can see any subset. There is no randomness in what adversary can observe. The eavesdropper or adversary can observe any T subsets of their own choice. So let me give a toy example to see how this is done conventionally and how we are going to make the cost smaller. So let's think about 2 secrets. So there are 2 elements from 2 integers, which we want to share into 12 integers. In such a way that the security threshold should be 4. So this is typically done by combining the secrets with random masks or random keys. So one needs to mix secrets with at least 4 random masks, as Shannon told us in its celebrated work. And how Shamir does it is by forming a polynomial whose coefficients are secrets and random masks, and evaluating this polynomial on 12 distinct non-zero points. So an evaluation of this degree 5 polynomial is going to be a share for each client. So if you want to think from the matrix algebra, I mean, again, I'm considering integers modulo 13. And then if you want to think from matrix algebra, just multiplying this by a Vandermonde type matrix, where each alpha I needs to be distinct non-zero integers. And then security follows from the properties of the polynomial. In particular, if you consider any 4 shares, then it doesn't give any information about the secret, because for every possible realization of secrets, there is a polynomial which can result in the same evaluation. So this evaluations could have been from a random polynomial, and these 4 shares cannot tell which polynomial would be used to compute these evaluations. And this can be made formal, but this is the intuition about security. And recovery also follows from the fact that this is polynomial. So let's say there are 6 shares which are at the disposal of the server. It can simply interpolate this polynomial. It's a degree 5 polynomial. It can be interpolated from any 6 points. In general, what you are essentially doing is solving a system of linear equations. The shares which are present is your right hand side, and you're solving for the secrets and the random masks. And this can be done efficiently without solving this. I mean, we're essentially solving this linear system by exploiting the structure, and one can do Lagrange interpolation or Newton interpolation to recover the secret. But the cost of interpolation is quadratic in terms of the number of shares. So that's where the quadratic cost comes into the picture. Now, the question we are asking is that for us, these dropouts are not worst case, they're stochastic. So can we leverage that and avoid polynomial interpolation to cut down costs? Right. So I'll tell you how we can do this, focusing on this toy example. Right. So for this, I'm going to take a signal processing perspective on the Shamir scheme, and I'm going to make 2 changes. So the first change which I'm going to make, which is a simple change, but it helps us later, is I'm going to evaluate this polynomial on roots of unity. So Shamir evaluates it on any distinct non-zero points, but I'm going to evaluate it on roots of unity. And this is finite fields, so roots of unities are slightly different, but you can keep your standard signal processing hat and just think of this as standard roots of unity, right? So our Vandermonde matrix, now the generating elements are the roots of unity. So the first thing to notice here is that as soon as we take our evaluation points to be roots of unity, we can compute the shares efficiently, because this polynomial evaluation is nothing but a Fourier transform of a signal consisting of secrets concatenated with random masks followed with a bunch of zeros. Right? And in fact, this is the approach Blehart's book takes when teaching about Reed-Solomon codes. So immediately we can use fast Fourier transform, which is essentially the divide and conquer, the celebrated approach to reduce the cost of computing shares from order n square to order n log n. Right? So just choosing evaluation points to be roots of unity helps us to reduce the compute cost of constructing the shares. How about recovery of the secret? Well, if there were no dropouts, great, right? Because we can simply use inverse fast Fourier transform and get back the secrets again in order n log n time. However, in practice, there are dropouts. And when there are dropouts, we cannot use this divide and conquer type ideas of FFT, because we cannot do this 2-point IFFTs and then stitch them back. We have missing points. So the FFT ideas don't work out. And then we have to go back to our polynomial interpolation perspective. There are asymptotically faster algorithms for polynomial interpolation, which are subquadratic in cost, but they're more theoretical in nature. Their constants are huge. And in fact, this was the key motivation stated in the celebrated paper by Luby, Mitzenmacher, and Urbanke and others to propose LTPC codes, that this fast interpolation schemes are theoretical in nature and we need something more practical. So how to deal with dropouts, right? Again, now we are going to leverage the fact that our shares which are dropping out are random. And to leverage this, what we are going to do is we are going to change the structure of the signal, right? So in the Shamir's case, our signal consists of all the zeros at the end. Now I'm going to change the way I construct this signal. And in particular, instead of putting all the zeros at the end, what I'm going to do is I'm going to disperse these zeros judiciously throughout the signal. And I'll tell you how we are going to do it and why we are going to do it. But the key difference from the Shamir's or the conventional secret sharing scheme is that the zeros are not all at the end, but they are dispersed through the signal. If you're still thinking from the polynomial perspective, then instead of degree 5 polynomial, now we have a degree 11 polynomial, but it is a sparse polynomial. So instead of a low degree dense polynomial, what we are using is a high degree sparse polynomial and evaluating it on the roots of unity. Right? So let me tell you how we decide where to put zeros and why we are doing it. So let's see how we are doing it. And for that, let me label these with coordinates. So the numbers here denote the coordinate or the index. So you can observe that the zeros are placed at the multiples of 3 and 4. 3, 6, 9 are zeroed out, 0, 4, 8 are zeroed out. Why am I doing this? Right? So let's understand how this helps us in recovery. Right? And let's do a signal processing 101 proof to show that this zero placement introduces parity checks on shares. So let's do a proof for this toy example. So let me consider a subsampled signal by subsampling it by 4. So it's a signal with coordinates 0, 4, and 8. By design, this is an all zero vector. So if I take a Fourier transform of this is going to be an all zero transform. However, we know that the transform of the subsampled signal relates to the original Fourier transform via aliasing. In particular, each value of the subsampled Fourier transform is a scaled value of the sum of certain spectral coefficients. So here, this is the spectral coefficients 0, 3, 6, and 9 must add to this value, but this is 0 by construction. That's why what we have achieved is there are small parity checks in our shares, and we are going to leverage this to recover from the missing shares. So let me take a pause here to make sure that this notion I've been able to convey, and if there are any quick questions, I'll be happy to take.
As I wrote, you've just blown my mind. Amazing.
Oh, thanks. Thank you, Anand. So let's try to understand these parity checks in a more rigorous manner, and for that, just considering a slightly different visualization helps. So instead of viewing these signals as one-dimensional vectors, let me view them as in a two-dimensional grid, right? So what I'm going to do is represent these coordinates in an XY plane, where the X coordinate is the index modulo 4 and Y coordinate is an index modulo 3. So this is possible by Chinese remainder theorem because 3 and 4 are relatively prime. And now you can see that our zero placement was on x-axis and y-axis. And also my secrets were placed in a peculiar manner. And in fact, the zero placement helps us in recovery, and the placement of the secret is crucial for proving security. But let's focus on the recovery for now. So the parity checks induced by the aliasing, when we view them in a two-dimensional grid, what has happened is each row sums to 0 and each column sums to 0. So you can see that the shares are, if I take the coding theoretic parlance, then the shares are essentially a code word of a product code with component code being single parity check code. So don't worry if you're not familiar with the coding theory parlance. What we have achieved is that in our shares, when we arrange them in a two-dimensional grid, each row sums to 0 and each column sums to 0. So how can we exploit that? Is when dropouts occur, if a row has at most one missing share or a column has at most one missing share, we can very simply recover it. And this is known as a peeling decoding in coding theory. We can keep peeling the missing shares, and it's well known that when the dropouts are random, then the peeling decoder succeeds with high probability, and it is computationally efficient. So our compute cost is mainly dominated by the fast Fourier transform, and we can recover the secrets in order n log n time. Because once we do iterative decoding, we have essentially recovered all these red circles to green circles, and the green shares are a Fourier transform. So we can take inverse FFT, and that's how we can recover the secrets in order n log n time. And so that's how we can reduce the compute cost of recovery from order n squared to order n log n. Right? So this was a very toy example. Let's consider a toy example which is more of a practically relevant, but I'm going to consider 10,000 users. This is a peculiarly chosen number because to be able to view this in a two-dimensional grid, I want to be able to write or represent my secrets and shares in terms of a product of two relatively prime or co-prime integers. That's why it is, we cannot choose any arbitrary integer, but this is a minor design thing. We can always choose the number of users to be few smaller or larger, right? And our zeros are going to be not only on X and Y axis, but also rows adjacent to X axis and columns adjacent to Y axis. And this peculiar zero placement ensures via aliasing that when we represent shares in a two-dimensional grid, each row is an evaluation of a low-degree polynomial. Or in other words, each row is going to be a code word of a small Reed-Solomon code. And same with each column. So we are going to do the iterative bounded distance decoding for our dropouts. And once we get all the missing shares, we'll take inverse FFT. So how we assign areas to zeros and secrets and the random mass determines our thresholds. So we can do a trade-off between the number of secrets, the security threshold, and a dropout tolerance. So let me give you more intuition into that. So these are the numbers we aimed for, right? 10% security threshold and 10% dropout tolerance. So all you want, the take-home message from this slide is that the number of secrets is the area of the blue region. The security threshold is proportional to the area of the green region, and the dropout resilience is proportional to the area of the gray region, which were our number of zeros. And we can change how large is our areas to have a trade-off between these thresholds. So I can make gray area larger to have the dropout resilience against 15% dropouts at the cost of sharing a smaller number of secrets. And as I will mention later, the number of secrets is directly proportional to the communication cost. So if we reduce the number of secrets that we can share, we are increasing the communication cost. So we are achieving a trade-off between the communication cost, security threshold, and dropout resilience. Of course, you can think I'm conjuring these numbers out of magic, but we can do this all formally and have precise characterization of this trade-off. But these are details, right? I don't want to scare you off with the notation here. The take-home message is that by carefully choosing these design parameters, or in ML terms, hyperparameters, deltas, alphas, and betas, we can achieve a wide range of trade-off between security threshold, dropout resilience, and communication cost, or the number of secrets. Right? So I want to mention in a couple of minutes the proof ideas for security, because even though we introduce small parity checks via aliasing, we want to make sure that there is no leakage. Right? This local dependencies shouldn't leak any information about the secrets for a given threshold. And this turns out to be the most intellectually challenging part of the work. And I'll only give you the high-level ideas. I'll be happy to talk details offline. The first step, where we rely on some of the results from Salim and Emina, which essentially showed that information theoretic security guarantees can be translated into linear algebraic conditions. And this is proven using first principles of information theory, the Shannon inequalities. So our task essentially becomes to show that the columns of our Fourier or van der Moon matrix, which multiplies the secrets, they lie in the span of all the remaining columns. And here we are going to use the fact that we have a van der Moon matrix, and there is some kind of invariance property, meaning that if a certain subset of columns is linearly dependent, then if we shift these columns, then the dependence preserves, meaning that if suppose first three columns were linearly dependent, then if I shift everything by one, then second, third, and fourth will be linearly dependent. So this can be shown using standard infotheoretic arguments. But this is where we have to spend most of our intellectual energy. What we can show is when we are sharing a single secret, then we can achieve the same threshold as Shamir. However, when we are sharing multiple secrets, then there is a gap between our security threshold and Shamir's security threshold. So we believe it's partly due to the limitation of our proof technique. So it's an open problem to tighten the security threshold of our scheme. And in fact, I'll be happy to talk more offline on the challenges here and how information and coding theorists and security enthusiasts can help us in tightening this gap. All right. So here is the summary of the secret sharing scheme, where we use ideas from iterative decoding as well as algebraic codes. The iterative decoding helps in recovery, and the algebraic or van der Moon structure helps in proving security. I should point out that there are applications beyond federated learning, even though the focus or the main motivation behind proposing this scheme was federated learning. But this can be used in any secure multi-party computation or any secure statistic problems. So let me take again a 1-minute pause to see if there are any quick questions. And if not, I'll move forward with secure aggregation and federated learning. All right, so in the remaining 10 minutes or so, I'm going to tell you how we can use secret sharing to perform secure aggregation. And then we'll see how to do privacy preserving federated learning, right? So here we are going to essentially use a secret sharing as a primitive, and the ideas here are fairly standard machinery in multi-party computation. So this is how secure aggregation works when we have a secret sharing scheme. What each client does is it treats its model parameters or weights and biases of a neural network as secrets and uses FastShare or any secret sharing scheme to generate shares. And then it is going to transmit these shares to the server. Now, of course, we want to achieve privacy against honest but curious server. So you cannot give these shares as plain text to the server, but we need to use some standard encryption. So this encryption is, you can think of it as a standard public key encryption. So you encrypt the share, send it to the server. Server simply relays the encrypted shares to appropriate clients. So at the end of round 2, what happens is each client would have received encrypted shares from all the other clients, right? So what each client does is it simply decrypts the shares, and then it has a set of shares from all the remaining clients. It aggregates or sums the shares and sends this aggregate share as a plain text to the server. What server does is, by using this summed share, it just uses the recovery algorithm of secret sharing, and it obtains the sum of model parameters. So here we are leveraging the linearity of the Fourier transform or polynomials to do the aggregation. So essentially what happens is, if we sum the shares, then they correspond to the share of the sum of secrets. So the summation or aggregation is essentially happening at the client side when the client aggregates the shares. So you can think of it as the aggregation is happening in the Fourier domain or in the secure domain, right? So, and then you decode directly the aggregate shares. So in this way, you don't leak anything about the individual shares or the secrets, but you only learn about the aggregate shares. Of course, I'm sweeping many details under the carpet, but the key idea here is to just leverage the linearity of the Fourier transform or the polynomial-based secret sharing schemes. In general, one can use any linear secret sharing scheme to do secure aggregation.
So I guess one quick question is, this is linear, but in the finite field.
Excellent question. Yeah. So what's with the machine learning, right? And that's where I'm coming at. That how are we going to handle the real numbers?
Mm-hmm. Okay, I'll just wait then. Yeah.
Great. So for one needs to prove security of this aggregation as well. Oh, there's a question on chat from Fangwei saying that does any pair of clients have to share a key? So there are two ways to do this encryption. One can do pairwise secret keys, and you can use cryptographic ideas like Diffie-Hellman key exchange, but one can also use public key encryption. So each client can have a public key, and then you can, in that way, you don't need to share any keys. So it depends really on the cryptographic implementations, whether you want to go for pairwise shared keys or whether you want to go for a public key encryption. All we need is to encrypt the shares from the server. So pairwise keys is not necessary, but one can use it, and that gives certain costs. But again, we use encryption as a black box, so that doesn't add up to our costs. All right. One needs to prove security for secure aggregation as well, and this is proven using tools from secure multi-party computation, where we want to show that a view of colluding parties is only a function of the final aggregation. These kind of proofs are fairly standard in multi-party computation, but we need to do them here, and we can show formally that the secure aggregation is indeed computationally secure and we can show that there is a computationally bounded simulator which is not going to learn anything beyond what the result of the computation is. So let me not go into details, because these building blocks are fairly standard, though there are subtleties and we need to deal with it. The high level ideas are standard. So let me skip it because I'm running out of time. But come to the point of doing it for machine learning, right? So Anand has raised this point where I want to go at, that these are real numbers. But even before that, I started the talk saying that there are millions of model parameters, right? And then I'm saying that you treat your model parameters as secrets. But the number of secrets is bounded by the number of clients, which is in thousands, but number of model parameters is millions. So how to deal with that? It turns out it's very simple. You're just going to repeatedly use the scheme. So you take your first est values of your model parameter, use FastShare to generate n shares, and keep doing it repeatedly. And it turns out that because the number of secrets is a constant fraction of n, the communication cost remains order L. So that's where if your number of secrets is large, then you can save in terms of communication costs. So in our toy example, we have to pay 5 factor more, but still this is the communication is still in millions. It doesn't blow up with the number of clients, right? It's still order L. The same thing happens with computation cost. Recovering or decoding each row is order n log n, and there are L or S rows, and we leverage here that S is omega n. S is constant fraction of n, and that's how the compute cost turns out to be order L log n. And this is how we get our final compute cost of order L log n and communication cost of order L. I brushed through this because this is fairly standard. I'll be happy to talk more details later if you have any questions. But the take-home message of compute and communication cost comparisons is that in terms of communication cost, we are order optimal. And in terms of computation cost, we are orders of magnitude better than the prior schemes. All right.
Quick question about this.
Yes, Anna.
In your round 2, the server sends to the client's share. And so I guess I couldn't quite understand how much that downlink, that downlink is using, because it seems like you'll have multiplied by the number of clients.
Yeah, that's correct. So here I'm plotting the cost as the per client cost. I mean, plotting in the sense. So the cost at the server is n times this.
Okay.
So the downlink cost is just n factor more.
Oh, right.
N
So
is
the first column is computation, and the second column is
yeah. Sorry about that. I'm
okay.
computation at the server. Yeah, there is an asymmetry, but there's a
it's
reason
okay.
for
I
that.
Can't read. That's all.
No, it is a bit confusing, but the reason behind that was that the computation at the server has been the main bottleneck, and the computation at the server and client, they're not like n factor, right? They're different. I have a table where I also have computation at client, but it is not as simple as dividing this by n is not going to be the computation per client. But communication and per client and communication at the server is just they're by factor n apart. Right? So I have written here computation at server because they were the most limiting factor in the prior art. The computation at client, people have already kind of somewhat reduced it in the prior. But that's a good catch. Yeah. All right. So in last 5 minutes, let me mention how are we going to do this for machine learning, right? Because I've been talking about things on finite field, but in machine learning, we have essentially real numbers. So how are we going to deal with this? So the first thing we are going to do is, even though we can use our secret sharing multiple times and handle arbitrarily large model updates, it is still computationally inefficient when your L is large. So the first thing we are going to do to make this scheme practical is use some form of compression, right? And in particular, we resort to sketching because in machine learning community, it has been shown that you can sketch these model updates heavily and this still doesn't impact the accuracy by that large. So think of it as the million dimensions. So if this is order D, then the sketch is usually order log D. So this is just a compression. We choose this specific subsample randomized Hadamard transform as a sketch because this helps us in doing quantization. because our secrets need to be in finite field, we need to first clip this model updates. And in fact, this is inconsistent with differential privacy type things, because the gradients or model updates are typically clipped for differential privacy as well. So this is standard clipping, and then we are going to do quantization. So definitely, this is an open problem, how we want to do clipping and quantization. Do you want to do fixed point representation and then do that? There are interesting open problems here. Our goal was to first show that this is practical, and that's why we have considered very rudimentary clipping and just quantizing it to nearest integer. But this is a definite open problem in terms of how to choose clipping and quantization to map from real numbers to integers modulo prime, so that your impacts on the accuracy are smallest. Right? But for my simulations, I'm just doing very simple clipping followed by simple quantization.
Another question then, actually. So are you then restricted in your field to use a prime field and not a power of prime field, because you need that cyclic structure in the additive domain?
It's not needed. So irrespective of whether I use a prime or a extended power of prime, I think where you are hinting at is there may be modular wraparounds, right? Because the aggregation happens in over the finite field.
Right.
So I need to, so these, my quantization and clipping are going to be my hyperparameters, and I want to choose them in such a way along with my field size. So these three are hyperparameters, and I want to choose in such a way that there are not many modular wraparounds which can cause divergence for machine learning.
Okay, but it's not restricting the type of field that you use. You can
no, it's not. Yeah, because once we can have, once we have integers here, we can map it to higher field, like extra prime power fields as well. So there will be an additional mapping from integers to that, but that can be taken care of. It's isomorphic, so we can do those things.
Okay.
But that will add a bit of complexity, not in terms of the number of computations, but you need to do that mapping and remapping. So keeping it integers modulo prime keeps it much simpler. Right, so when we do this, does it work in practice? And I'm going to show you, I guess, indeed it works in practice. And for that, we have simulated it on this LEAF dataset, which was jointly considered for federated learning by Google and CMU. So the first task is image classification, and the second task I'll be considering is next character prediction. There are a bunch of details here, but the high-level message is we are considering a machine learning case with million parameters, and we are going to consider roughly 2,000 users. And in federated learning, they typically randomly sample a subset of users. So this is for if there are only some users available or not. This is typical in federated learning papers. So we sample 50% of users, just 1,000. These are peculiar numbers because we want to represent everything in a two-dimensional grid. So they are a product of two co-prime numbers, but think of it as 1,000 users. And each user is doing SGD for 20 epochs. We use our FastSecAgg with 10% dropout tolerance, 10% security threshold, and I'm using this prime 1123. So I do sketching to reduce from million to 100,000. So I do compression by 10%. I clip everything heavily to -2 to 2, and then quantize to nearest integer. So the blue line here is, I'm calling it Oracle because it is as if the secure aggregation has no impact. This is like a vanilla federated learning. And this orange line is using our fast secure aggregation, where if in a given iteration, if there are more than 10% dropouts, or if your peeling decoder gets stuck, then we just discard that round and move to the next round. So considering both that, how many number of global rounds it takes to retain some accuracy, we can see that we are only 2% away from the vanilla federated learning. And this 2% is because of the sketching and quantization. It's open problems. Can we improve on this in a machine learning signal processing way to cut down this cost as well? The same story for next character prediction. Here we are considering a smaller number of users because it takes a long time to train these things. And without going into any details, the main message is here we are 4% away from vanilla federated learning. And again, improving this is an open problem in terms of how can we do quantization, sketching, and mapping to finite fields in a more clever way in order to reduce this hit we are taking in terms of accuracy. All right, so with that, let me summarize. So in this talk, what I presented is a scalable secure aggregation protocol with federated learning as the key app. But even though we focused on distributed learning, the secure aggregation protocol can be used for applications beyond federated learning. And the core intellectual component was a novel secret sharing scheme based on fast Fourier Transform, which on itself has applications beyond secure aggregation. It's a new secret sharing scheme with worst case privacy guarantees, but stochastic or average case dropout guarantees. The paper is on archive, and there are interesting future directions. One more from info theory, coding theory point of view is how to improve the security thresholds of FastShare as a secret sharing scheme. From cryptography or MPC point of view, how to be secure against malicious adversary, because in our case, all the parties were honest but curious. And from the machine learning and security intersection point of view, because the aggregation happens in the finite field or the shared domain, how to make sure that the modular wrapping and quantizations are not causing problems with accuracy. Because we had to do hyperparameter tuning on the clipping and quantization and the field size. That's how we could achieve this accuracy. If we arbitrarily choose a field size, clipping window, and then the algorithms may even diverge. And at a more high level, the interesting direction here is to develop protocols that can have a three-way trade-off between privacy, security, as well as fairness. And how to do that is an interesting direction in general in distributed machine learning. So with that, let me stop, and I'll be happy to take any questions.
Thank you very much, Swanand. I know there were some questions during the talk. Are there any other questions?
I guess I have a quick one quick question. I guess on your security threshold, I must have missed it somehow. What is the maximum collusion threshold that you could deal with? Or
yeah, good point. So that is a design parameter for us. So we can do with any t up to 50%. T meaning the threshold. Up to 50%. Okay. Yeah, but then the case is for Shamir, t+1 is the recovery threshold, but for us it's going to be a large gap. And also we cannot go beyond 50% in some. So what I presented
I thought it would be a third. I thought it would be a third. So 50% sounds amazing.
In practice, it is third, because if I want to get any meaningful recovery threshold, then I can go until up to third. If I approach 50% security, then my recovery will be like constant number of dropouts, which doesn't work. It's not interesting. If you want to keep constant fraction of dropouts, I can go only until third.
And I guess one other question is, I mean, so you rely on the dropouts being random, but the server can essentially force dropouts to be random.
Excellent point. So our security guarantees still hold even if the dropouts are adversarial, but we don't give any guarantee for recovery. So if Google or any federated learning or aggregator wants to be adversarial, they won't learn anything, but they won't be able to do their computation as well.
Right.
So
no, but I meant you could simulate you could simulate the average case, because the server can choose who to talk to. So
if server is malicious in that, it falls into the malicious security. If
I'm not talking about being malicious. I'm saying if you're relying on a stochastic assumption on the dropout, the server can simulate stochastic dropouts on their own.
No, I see your point, but the issue is if there is some external adversary which kind of drops out some people arbitrarily, right? Then we can use Shamir's scheme for secure aggregation, but we cannot use FastShare or FastSecAgg because we don't guarantee recovery.
Right. Okay.
Right, so that's the case. The server, it's good for it if there are no dropouts. You don't want to simulate it because you can directly use FFT if there are no dropouts. Okay. The dropouts are coming from the practical reasons, and that's why we want to deal with them. So that way, server simulating dropouts seems slightly impractical, but yeah, in theory, I see your point.
I also have a question. Yeah, sorry that my video has a problem.
No problem.
So there's one thing I wish you could clarify about the recovery part. So if I understand correctly, the client model can have a large number of parameters, and your mechanism can make sure the aggregator or adversary cannot, use this protocol to recover all the parameters from the client model, like one client model, right?
Correct.
So, for example, it is possible you have like some knowledge of part of the parameters from one client, but that is okay because you cannot use it to do model inversion or any other kind of advanced attack.
I see your point. Excellent point. So our security guarantees currently are that you learn nothing about any individual client. But this is a very interesting point you have raised, whether it is possible to design schemes which allow small leakage, which is not going to be useful for adversary, but it helps in scalability.
Right.
So that's
exactly.
that's a very interesting open direction. In our case, we give complete security for every individual. In fact, every set of T clients we give complete security. But it's a very interesting practical problem. If we are going to allow small leakage, how can we exploit that further?
All right. Yeah. And thanks for the nice talk.
Thank you. Yeah. Thanks a lot.
Other questions? There is, it seems, there is a message for Mehmet in the chat.
Oh, thank you.
Yeah. Anyone else? So, Swanand, these putting zeros and looking in the problem in the spectral domain, is this just a convenient tool, or does it bring some unique insights, or both? And the reason why I'm asking is one can define a Reed-Solomon code that way.
Exactly. So in fact, in Blairhead's book, he introduces Reed-Solomon's codes in a spectral language. And if you look in the other way around, the shares being the signal and the signal being the spectrum, that there is a signature of the spectrum. It's like low pass, right? All the zeros are at the end. So what we are essentially showing is that we have a different signature where the zeros are dispersed, and now our shares are going to be a code word of a product code and not the Reed-Solomon code, right? So we can even think of it as just a code design way, right? How this helps us is because we can prove security by exploiting this structure of zeros by using the linear algebraic condition which you and Salim worked on, right? So there, this structure of zeros also helps us. So from the pure code design point of view, this is exactly extending the spectral way of thinking about codes. And what we are showing is that if you have all the zeros at the end, then it's the Reed-Solomon code. But if we put zeros in a peculiar manner, then we get a product code. Or in fact, we can also show we can get a locally recoverable code. And in that case, our constructions are isomorphic to Tabo bar constructions for certain parameters. But this helps us in proving security as well. So there are two insights from it. One is it is just designing different types of codes, but you don't need a zero placement to design codes in that way. Where we really leverage is to show security. And there we use the two-dimensional visualization to show that certain columns are in the span of others, because the zeros are essentially missing columns from the Van der Waals matrix. So that's where it helps us.
I see. Thank you very much.
Sure.
Any other questions? All right. So now I will allow Swanand to go to the other Zoom link, and people who are meeting with him will join when their time slot is up. And thank you all very much. And in the end, I would like to just thank the students. And if your cameras are working, maybe you can just wave to all of us. Pei Peng, Batol Taki, and also Muhammad Zulkaranian. So thanks, guys.
Thank you, Amina. Thank you, everyone. If you have any more questions, please feel free to email me. Thanks a lot for this opportunity.